As a reminder, please finish voting for group names. We'll announce those on Friday. Tomorrow we have our office hours again. Also, no in-person lecture for this coming Monday, the 24th. Again, there may be some video content depending on what material we go through or other work problems and stuff at that point, but we won't have an actual meeting in here today. Any other questions before we get rolling on that? What's that? It's okay. Last class. We are diving into our electrophilic substitution. We now can put nitro, sulfate, halogen, and carbon. Carbon being the last series in that point. Those are your main groups you're going to be decorating around the aromatic ring. The ones that we call carbon substitution, that's our Friedel-Crafts. And we just touched on this idea of rates of reaction. So, for these two, how might you make these? We're both making carbons. We're assuming we're starting from benzene. What is a better choice? Alkylation or acylation for each and why? So take a minute, think about that, and discuss that with your partner. Okay, so I'd like to hear your vote. This one here, alkylation or acylation? What's the better choice? Acylation. Why? Yeah, your key marker, right? If you're saying this comes from benzene, that's the bond you're cleaving, right? The carbon aromatic bond. We're starting from benzene as our nucleophile. That makes this guy, maybe some halide, let's say the bromide, my electrophile, right? That would, if this was alkylation, I'd be coming from a simple halide component. That means the electrophile, after we treat it with like aluminum tribromide or iron tribromide, would effectively be this primary carbocation. The problem with any primary carbocation, if it has the ability to form a stabilized center doing a hydrogen migration, a carbon migration, it will. So interesting conversation about this one before. Is this new to us? No. What's interesting about what we're doing here with these kinds of reactions, we now have a reagent, aluminum trichloride or iron tribromide, that is powerful enough to make even primary carbocations no matter what you care about. This is now a powerful enough reaction that this is going to happen regardless. You can now rip off primary bromides to make these carbocations. And the result of that, if you form this primary carbocation, it's got to find a way to stabilize itself. Before, if you say, well, they just don't form, that's a rate question, that's a stability question. Here we have a powerful enough reagent that it's going to happen. And then if it forms this primary center, it's going to rearrange. So we would not be able to directly address this because the center of the attachment point is effectively from what used to be a primary center. We can't do that one by alkylation directly. It's a bad choice. The alternative would be acylation, which means we're coming from this fragment, let's say the chloride. That gives us an intermediate, something where we would have the carbonyl. We form the ketone as an intermediate, which we then carry through reduction. So it's a two-step process. But a result of that is we can generate a primary center if we want to. On the other side, alkylation or acylation over here. Yeah, that one's okay for alkylation, right? Again, that would be my aromatic ring and the bromide, which would effectively give me a secondary carbocation. Fair. That one works. That one's appropriate. At least it's not primary. Just as a note, does that secondary do anything? Are everybody worried about this to make any of the products? Could this migrate to at least as stable of a carbocation as you have already? What I mean is, it's secondary. Can I make a different secondary from this? Yeah, it possibly, and this is, you have no choice, but that's possible, right? It could hop over 1. It means that in this case, alkylation will work. That will get you your product. Warning, be expecting some rearranged product as well. The asymmetric nature of the structure you're putting on there, by consequence, means it could hop. Now, it's not going to be as bad as the first case. We're not going primary to tertiary, but it is going to be something you may see as a byproduct. The opposite is, well, wait a minute, maybe acylation is the solution to all our problems. No, because if I tried to do this by an acylation, remember, what we're saying by an acylation reaction is the corresponding acid chloride became my precursor. The oxidation state of the attachment point here must be something like an acid chloride. And you'd have to have the two groups attaching to it, which gets me a methyl and a whatever, propyl on a center with 5 carbons. A secondary center by attachment could never have come from an acylation because the precursor, the acid chloride, is the wrong oxidation state. There's no way I could generate a ketone at that center and then reduce it. We could have gone to the ketone. Another way, if I really going to stick to acylation, I could have generated the ketone first. Let's say I made this first, and then added the methyl group by way of, let's say, a Grignard reaction, and then get rid of the oxygen. It's possible to do it under other steps. We'd have to do something else, but it's not as simple as, oh, I'm just going to use acylation. That'll get me any product I want, right? We have to do other modifications, but that's back into ketone territory again. Okay. So these are the primary, oh yeah, please.
What is the driving force for like, in the alkylation step, why does secondary just go back to secondary? Like, what is like the driving force?
It's not a driving force. You're right, they're equal in energy, so it's not going to be a major product distribution. It's just if I have a secondary, the reason this goes back to why are things stabilized, hyperconjugation of adjacent groups are partially delocalizing, which means the hydrogen and carbon adjacent to that carbocation are kind of losing some of their energy density to that carbocation. It's possible that at least if I'm already kind of sharing a proton to kind of help that one there, that proton may decide, I'm going for it, right? And at least it's not energetically worse. There's not a strong driving force other than concentration, right? That's just a little bit probability distribution. Just mentioning it as if you run this reaction, you see that other one, don't be surprised. I warned you, that's all. All right. So now that we have our fundamental reactions to decorate an aromatic ring, we're going to talk about multiple decorations. This is orders of addition and using the various things we've called in terms of activation and deactivation. The group we add changes benzene and either makes it more nucleophilic or less nucleophilic based on its donating ability, both in the aromatic, in the pi and sigma sense. On top of it, we can also do things like polysubstitution, many reactions at once if we want. The problem is different groups will have different sensitivities to their ability to do the reaction based on how electrophilic the parameter is. And there's some that we can and cannot do, either the place we're trying to put on the ring or the ring or the modification we're trying to make. So we finished off with this last time saying, what happens to the barrier? Think about this. This is always going to be our slow step, just like in an SN1 reaction, making these delocalized carbocations. Two things we're doing here is we're paying a price to break down the aromaticity, but second, it's very high in energy, right? We're making a carbocation at the species. So if that first step is our slow step, again, if you think about this in a sort of energy level diagram sense, I'm starting out here, I have to make a large jump to some intermediate, and then down to product. This will always be the delta G double dagger that I need to get over. That's the rate limiting property for these reactions is this first one. So anything I do to modify the stability of this will actually impact that delta delta G. Think of it, this is what's known as what we call the Hammond postulate. If I draw this down, that intermediate, if I drop its energy, I will drag the transition state along with me. And vice versa, if I increase the energy of that intermediate, the transition state changes as well. So although the conversation we're making is about the stability of an intermediate, it impacts the rate. Because if I was to take that intermediate, decrease it, stabilize it in some way, the same starting material will now have a lower barrier here. So by lowering the delta G between my starting material and my intermediate, I consequently are going to lower the delta G double dagger to the transition state to that same intermediate. This is what we call, again, it's called Hammond postulate, but the idea here is that if I understand the structure and the energy of some high-level species, the transition state near it will also have similar energy as well. So this is a 2-for-1. We can look at the stability of that intermediate and then come up with ideas of what might happen to the rate associated with forming that intermediate, right? They're linked together. So this is where the substitution pattern, what goes on this ring, will impact the stabilization of this carbocation. It's not much different than we've talked in the past about having a delocalized carbocation. Donating an electron, or donating and withdrawing groups can help or hurt the positive charge that we're building up on this ring. First principle, right? What we call activating groups or deactivating groups are referring to the ability of adding that group to make a substitution, the subsequent substitution, faster. So instead of starting with benzene, where G is no longer hydrogen, if G is some group that goes on there that makes addition of another group, whatever comes after this, faster, we refer to G as a donating group. So a single substitution that makes the next group on quicker, we call it donating. Likewise, if I put something on benzene and the next substitution gets slower, we call that group deactivating. More or less, donating or activating and deactivating is talking about electron donating as being an activating group because we're making it more nucleophilic, and a withdrawing group will be a deactivating group. So it comes down to the properties of which group it is in terms of its relative electron donating or withdrawing potential. The last is what we call orthopara or meta. Orthopara just means where the next group is going to go. This is our para position, this is our ortho position, and it's always in reference to the group that is already on there. So if a group is on a ring and the next group gets added to the orthopara position preferentially, we call the group G an orthopara directing group. If having G on the ring will add the next group into, sorry, let me do it in different color. If having G on the ring adds the next group in the meta position, we say G is a meta directing group. Now what you'll find is these things typically move together. Activating groups, things that make reactions faster, are typically also orthopara directing. So there's a link between these two. If something is more nucleophilic, it will typically also be an orthopara director. And we'll show you what that means in terms of their energies later. And vice versa, if something is deactivating, it typically happens to be a meta director. So it's not perfect. There's a little bit of nuance there because what we're talking about is rate and selectivity. There's a little bit of a differentiation, but they do kind of move in parallel. So you can work out these pieces. So this is just the word summary written down of what I just went through. Activating groups cause the rate of aromatic substitution of the next group to be faster. Deactivating makes the rate of a substitution slower. And again, when we're talking about rate, we're talking about the stabilization of that intermediate. That's why the other two things come together. Being an orthopara director means the next addition will happen to be in these, either the immediately adjacent or across from whatever that substitution is. And if it's a meta director, you're going to get higher yields for this meta position. One other thing that you're going to run into too, just as a sort of visibility, what we usually see, orthopara is the result of a helping action. In other words, having a donating group on my ring, I will stabilize or help the addition to my ortho or para position. Meta is kind of the consequence that happens when you have no other help. So don't think of it as, well, one group is going to help meta and one group is going to help orthopara. What you'll see as we go through the resonance diagrams, orthopara comes from a helping action, donating electrons stabilizes orthopara substitution, versus meta is the best option given bad choices. It's not that it's suddenly helping you to be meta. Okay, let's look at these two. So we're saying we start off with a group on the ring. whatever that group happens to be, and I'm going to substitute at the ortho position. So I'm doing the test here of saying, imagine I start off here. I want to add some electrophile to my ortho position. This is the sigma complex that I must form in order to make it through to my ortho product. I'm using that ortho position to create this substitution. The sp2 center turns into this sp3 center right here. And we know after deprotonating that gets us to our product. Great. Now think about these two things. If this is a donor group, which means we are donating electrons at that position, do we make the sigma complex happy or unhappy? So who's happy? Nobody's happy. I get it. No. Who's on the side of happy? Yeah. If G is a donating group, notice where what happens when I make this substitution. Substituting here creates positive charge at these three positions. Remember, this is a delocalized carbocation. Wherever we add that sp3 center at the 1, 6, and 4 position, 1, 6, and 4 on other sides of that new sp3 center will have a partial positive charge. Which means if I have a donor group right here, this interaction is being stabilized. The positive charge that would be a result at that position has got a helper now that's helping it out. Versus if the G was never there at all, it has to just deal with the fact that there's a positive charge. So if this is a donor group, we're stabilizing specifically that interaction, which is going to generally lower the energy of the resulting carbocation, right? Opposite action. So if we have electron donating group, the complex will be stabilized. This specific geometry in complex is stabilized, which we mean is substituting at the ortho center is a good thing because we created a carbocation that has a stabilized intermediate, right? If G was electron withdrawing, the opposite is true, right? If G happened to be strongly electron withdrawing or even positively charged, what we've done is created a negative interaction over here. If we pull electron density away, we're saying the carbocation now has to deal with this immediate adjacent carbocation. We're putting two coulomically repelling things at that center. What we're going to do is generally electron withdrawing group will destabilize ortho substitution. So this is what goes back to this idea of if I have a group that can be a donor group, it's going to help this ortho substitution. Same wise, if I have a group which is withdrawing, it will hurt ortho substitution. Okay, let's do the next one. This is meta. If I start with the same starting material, but now I'm targeting substitution right here. I put the attack is at the position which is meta to that group. Okay? All right. Once again, let's do these two ideas. If G was donating, so I'm adding electron density here, what's it going to do to this complex overall? Good or bad? Okay, who's on the side of good? Okay, there should be more hands than that, because good is good. No. You're putting electron density into the ring. Good. Is it bad? Not really. Is it better? Is this interaction better than this one? Of these two, what seems to be more favorable? Donor group dumping charge into a center that is positive compared to donor group that's kind of threading the needle where the charge is kind of to either side. First one or second one? What do you think is a more favorable interaction? Yeah, the first one's probably better because the charge is physically located at the same carbon that the donor group is sitting at. So ortho sort of wins between these two. The meta, though, it's at least not bad. It can be slightly stabilizing, but it's not really destabilizing. It's kind of mediocre. So if we had to sort of rank them, in the first case, a donor group will stabilize, and we can call that a significant positive bump. this is a very good thing because we're taking a positive charge and we're actually donating electron density at the center that positive charge is built up. Over here, it's at least ambivalent. It's not really great. It's not really bad. It's still a help. It's better than nothing, for sure. But it's not going to be as impactful as the first case. Withdrawing group, what happens in that case? Let's flip the geometry here. Better, worse? It's kind of the same, right? Now you've got a withdrawing group, but once again, charge does not sit directly at that center. It's not better. It's not worse. It's kind of in the middle. This is basically meta substitution like this. If anything, it's a little bit bad because, once again, you're pulling electron density away from something that's already positively charged. But meta, that's why we said before that meta is kind of in the middle here. It's not being significantly helped, but it's also not being as badly hurt as the interaction we would have in this case. If I have an electron withdrawing group here, this is very, very, very destabilizing. So at least you've got sort of ambivalence, acceptance in that point. If we do the final one in para, so now I'm substituting over here. Once again, sp3 center gives you this 1, 3, or 1, 4, 6 kind of geometry of where that positive charge is going to sit. And we see the same interaction that a group here that's donating will tend to add charge right to where the center is. It's going to be stabilizing, which is going to be a significant positive bump. Opposite, if this happens to be withdrawing, it will be significantly destabilizing. And in the same way, building up a positive charge at a center where you already have significant withdrawing or positive charge will tend to be against. So what we're doing here is a scorecard. If I have a donor group here is going to work through and favor both the ortho and para substitution. Having something that's a donating group will tend to favor either of those substitutions because of a positive interaction here in the case of the para and a positive interaction here in case of the ortho. Meta is just the consequence of both. If we are trying to have neither a donor or an acceptor, not really help in each, this is your sort of best choice. If you have an electrophile which is so powerful that you're going to substitute this ring, meta is kind of the alternate. So what you typically will see is one of your groups is going to highly favor ortho-para or highly hurt ortho-para, with meta being sort of the one that results in the middle. Okay, let's practice this. Now, the thing with these activating, deactivating groups, changing the rate. This comes back to what we've seen with pi electrons versus sigma electrons. Remember, and this is going back to the discussion we had about the relative electrophilicities of things like an ester compared to a ketone compared to something like a halide. So of these three guys, again, back to last chapter, acid chloride, ketone, ester, which is most electrophilic? Yeah, acid chloride's going to win. What's next, ester or ketone? Yeah, ester's in the middle, ketone's on the bottom. And this is a consequence of a balance of, what's that? Oh, I drew it right. That was, yeah, that's the, I've mentioned that before. I used to be a defenseman. I've had, for a whole month, I couldn't actually speak next to a puck to the head. So every now and again, what comes out of here doesn't quite match. I apologize. So ketone is better, ester is on the bottom in terms of electrophilicity. Remember, this is a balance of a couple different properties. Here, the electron withdrawing nature, the sigma withdrawing of my chlorine, is really, really helping to make that center even more delta plus. It increases the electrophilicity at the center, makes it more reactive. Something like the ketone, these alkyl groups are effectively donors. Hyperconjugation helps to shield or donate back electron density into the partial positive center, the carbocation-like character at that pi center. Oxygen ends up being a kind of a mix of both. Even though it's a sigma withdrawer, it's a pi donor. Resonance on the electrons allows me to add back electron density and effectively shield the partial positive center, even though the oxygen is a bit of a sigma withdrawer. So a lot of the same principles you see here in terms of mixing is going to be what we see again when we play with the aromatic rings. The real principle here is if something can help via pi donation, that's going to be a helping point. So we're looking for things with lone pairs around the ring to give back charge. Things that are withdrawing are going to be positively charged things, not just inductively, but also a positively charged center like a nitrogen plus is a really, really powerful withdrawing group. Overall, this combination of both resonance and induction effects is what we have to sort of rank through. So let's look at this guy. If you look at aniline, draw the resonance structures of what the contributions might look like. So I have a lone pair. The lone pair if we draw the resonance structure, we're going to have some type of a zwitterionic structure here where we're using the lone pair to donate back into the ring and localize it at one center. Next one is down here, and then one more. Okay. By induction, carbon versus nitrogen. Yeah, sorry.
Are the ones that have the negative charge in the ortho position, are those not identical to each other?
Yes, they are technically identical. In terms of probability, if I named the carbons, carbon 1, 2, 3, 4, 5, 6, they are non-identical. What we're trying to say overall, the resonance hybrid that we would draw has delta minus, and delta minus, right? I'm explicitly mentioning them when we talk about all six, just in case the ring had an asymmetric center, right? If we had something else on the ring, we want to keep track of all three, right? But you're right. Equivalently, those two are going to be more or less identical in terms of relative energy or contribution, just because of symmetry here, for sure. But induction, it's going to be a small withdrawing group, right? Because of the electronegativity difference between carbon and nitrogen, if you go across the row, nitrogen is more electronegative. It will be a little bit of a sigma withdrawer, right? The sigma bond is going to pull back on this. But in terms of resonance, it is a donor. The overall impact here is that lone pair is being donated to the ring. We're going to have a higher concentration of electron density in this benzene than we normally would. And this kind of matches what you'd see for, again, if I was to just focus on this guy here, super close. What's this if you only focus on that? What is that? That is an enamine. Enamines are nucleophilic carbons. They're like nucleophilic carbons. That's kind of what this guy is. If you have a structure like this, it's just that now that we've got this aromaticity, it has a little bit different sort of energy. But in the same way, it is nucleophilic. And is nucleophilic at these three positions as a consequence of this point. So this is a donor group overall. We would expect a neutral nitrogen to be a pretty decent donor. Yeah?
I was just wondering what you wrote next to induction.
Small. Small effect. How about that? It's a small withdrawing group. So is it activating or deactivating? If we're adding electron density to this ring, what would you expect? Is this going to be an activator or a deactivator? It's going to be an activator. We're going to stabilize positive charges because we're adding electron density to this ring overall. So overall, this is activating. What kind of director is it? In other words, look at the pattern of where your negative charge is building up. Negative charge relative to nitrogen is where? Ortho, meta, or para? Yeah, negative charge exists at these three centers that relative to this are ortho or para. So this is an ortho-para director. So this analysis can be carried out with any of your functional groups. You take your benzene, you put your group on, you look at your resonance structures you could form here. Wherever negative charge builds up, that is where you will likely substitute with your electron density. So I have extra electron density in my ortho-para groups, it will be an ortho-para director. Because I'm adding density to this ring, I'm making it more negative overall, it is an activator. Okay, nitro is different. So here we've drawn out all the different structures we have for nitro. A nitro group, remember, is a formal charge as an N+. We have more resonance structures as a result of that. But since we have this formal nitrogen plus, look around the ring. How would we rank this? So first of all, via induction. Is this a withdrawing group or a donating group with regard to induction? We're saying that if I am looking only at the sigma bonding character right here, is this withdrawing or donating electrons at this center? Because it's positively charged. Right? This is a nitrogen that is already positively charged. This is going to be a withdrawing group. Resonance. Is it donating or withdrawing? Is it adding electron density or subtracting electron density in the pi system? Withdrawing. Everything is pulling out of this one. Okay. Activating or deactivating? Remember, when you're asking that question, you're saying, is this ring unusually dense in its electron density, or is it low in electron density? Does it have more electron density than benzene or less? Probably less because you've got this delocalized positive charge to start off. This will be a deactivator. What director is it? In other words, if I had to give this an electrophile, this is my starting material, where will the electrophile go? Ortho-para or meta? It's going to have to be meta. Because the ortho-para positions already contain a positive charge. I can't add an E+ to a center that's already positively charged. So however you want to do your analysis of this one, looking at the relative charge density where you start off, or the stabilization of our intermediate, this will be a meta director, and it's going to be deactivating. So this gives you two extremes. These are really the two kind of guideposts to look at every one of our substitutions. Nitro is the quintessential meta director. If you have a nitro group on a ring already, it means the next group that gets added will be in the meta position. If I have an amine on a group, a donating group by this kind of a lone pair like my amine, I am typically going to add density or add my next group in my ortho-para position. What about this guy? Again, we can do the full analysis later on, but methyl, what did we say methyl was? Is it an electron donating group or electron withdrawing group? So what would you expect just on that? If it's donating, is this going to be deactivating or activating? Right? And it's going to be ortho-para or meta? Yeah, that's the piece of it. And again, we'll go through and we'll draw out these structures. You'll see what those parts go. Same thing for aldehydes. Now, halogens I want to spend a bit of time talking about because they're a little bit weird. This is one of those points where we've got a tipping point. Halogens turn out to be much stronger in their induction. They are withdrawing. And that's a consequence of the electron density that we've got, right? The chlorine on its own is a pretty electronegative atom, and it sort of flips over on that tipping point that chlorine, halogens like chlorine and bromine, chlorine in particular, is a strong enough electron withdrawing group that you do feel this feature. It is an inductive withdrawer. Resonance, though, what do you guess? So if I had to draw out the resonance structures, I've got lone pairs. Is this a valid resonance structure? Welcome to second year. Valid with a very small v. It's allowed, not awesome. This is not what we would call a major resonance structure, but it is allowed. Especially when we start to move things like bromine, where we have larger electron density polarization. This is where the line between polarization and resonance starts to blur. And again, this is one of those things where the properties and the empirical evidence we have of how these things react is where we start to actually divide the line and say, where is something a strong donor or withdrawing group? There's an entire principle known as linear free energy relationships that came from these relative rates. So the properties we're seeing here are not something you would predict a priori. We run these experiments, we see where the groups go, and from that we make the decision about what is a donor and what is withdrawing. So this is not meant to say, oh, look at chlorine. Yeah, that's probably a donor. That's not how this happened. It's like the same thing. There used to be a joke of like, you're not sitting around going, I wonder if there's a point in the universe of infinite density. No, this is something where observation says black holes must exist. Observation of how these things react tells us what properties and density must happen. So we're using the theory of resonance here to fill in for the observation of how these guys work. It turns out chlorines are ortho-para directors. The only way to rationalize it, if I take a chlorobenzene and I run a Friedel-Crafts reaction, I will get properties. I get substitution that is consistent with attack there and attack there. So if I run a Friedel-Crafts reaction with chlorobenzene, the result of this reaction is I substitute ortho-para preferentially, which means the ortho-para positions must have more electron density than they typically would, according to benzene. It's minor, it's small, but this is where we start to have these gradations. This is not a quantized phenomenon. This is something that happens from these types of reactions. So in general, we bin halogens as ortho-para directors, but they are also deactivators. So this is where you've got a tipping point. In general, donating groups are going to be activators. That is true of things like O-methyl, of things like alkyl groups. Withdrawing groups are deactivators. Nitro, positively charged groups. Those are universal. Chlorine sits right on that line where it kind of helps out the relative negative charge, but it also slows down the rate of reaction. So this is where the relative amount of inductive withdrawing, but sigma resonance donating, the withdrawing character here is beginning to overtip what we saw with something like oxygen or nitrogen. And it's just because of the relative electron negativity of the atom that we're playing with. Okay, this is your awesome guide. Benzene is our reference point. This is neither donating or withdrawing because we're taking hydrogen as our reference. Anything to the right are our activators. And anything over here are going to be our ortho-para directors. So things like methyl group, OMe. What we have here is, remember, this is our hyperconjugation as our donor. Here we've got lone pairs as our donor. Neutral nitrogen, pretty good donor. Oxygen minus, wow, what a fantastic donor, right? This is a full negative charge to help stabilize a positive charge that might be in the ring. On the other side, halogens sit sort of in here. They are deactivating, but ortho-para directing. And then everybody else, after halogens, they are deactivating, but they are meta-directing. So that includes things like carbonyls, nitriles. Those are our resonance deactivating systems. Notice down here, though, so these guys are pi systems that are doing most of the work in terms of withdrawing. Nitrogen here is formerly nitrogen plus in nitro. Or this guy, positively charged nitrogen. Remember, basic centers like an amine, once I protonate it, I've used up that lone pair. It can no longer help me out, and it is a positive charge that's sitting on the ring all the time. Those are the worst things that you can possibly do. Now, there's something on this chart that should bother you. Do you see one guy that kind of shows up here twice? He looks really close. Same guy, really, really, really similar. I'm down here. Whoops. Bloop. No. I'm down here. I'm right here. Aniline shows up here twice. In its either protonated or deprotonated form. If I protonate aniline, I make a positively charged nitrogen. It's a formal plus. I've used up the lone pair. It cannot be used for resonance. If I'm neutral, aniline's a pretty good activator. The problem is, go back to our conditions. How did I put a nitro group on this ring? Do you remember what reagent I needed to add nitro to an aromatic ring? Nitric acid, and you're boiling it in the strongest acids we have, which means this guy, under those conditions, will only ever be my positively charged species. This is where these conditions you see here, the charge density, this is absolute truth. The one thing you have to keep in mind, though, is the conditions we do the reaction under can influence things. And the most common one you run into is protonation and deprotonation. The strongest activator we have is phenolate. We form phenolate by deprotonating the OH. But if I have to put a nitro group on there and I'm boiling it in strong acid, I have zero phenolate available. It will act like a base first. There are conditions we can use to apply this, but this is just both a mix of both what's physically practically possible coupled to our acid base. All right. So let's predict this one. Assume the reaction conditions are the same. We are going to add one group. So the first condition is fluorobenzene. I'm going to add chlorine using these conditions. Second one, that's my starting material. I'm adding this junk. This is Friedel-Crafts alkylation. Take a moment. Talk to the person next to you. Where does the group go? Okay. First example. What's your guess? It's a halogen, orthopara, or meta? Why? Halogen. Good job. Yes. It's a halogen. Because it's a halogen, it has lone pairs. Because I have lone pairs, I am a pi donor. I'm also a sigma withdrawer. Halogens class as deactivators, slower, but still orthopara directing. What's the group I'm adding? For those reaction conditions, what did I stick on the ring? What's that? Chlorine. Yeah, this is a chlorination reaction. These reaction conditions are going to make a Cl plus that will preferentially add ortho or para, not your meta. Right? Your meta direction here is hindered. And all we're saying is it is faster to do ortho and para than meta. The reaction is going to outrun the other two. Good. Next one, ortho, para, or meta. You have an OME. That is, again, a little bit of a withdrawing, not as bad. More of a donor. This is both an activator. Reaction will be faster. And it's going to be ortho, para directing. So you're going to substitute here and here the ortho and para groups. What's the group look like? I'm attaching it what? A primary, secondary, or tertiary center? Yeah, it's going to be a secondary substitution. like that, you're not going to get much of the meta substitution. This guy's out, meta. In both cases, the meta substitution will be disfavored relative to the others. Question, if you had to guess, ortho-para, what's the ratio? 50-50, more one, more the other? Electronically, they're basically similar, right? And this is something that there's a very, very tight balance. Turns out, sometimes ortho wins because I have two of them. Probability can help me on the ortho position sometimes. What might help me favor the para position? Sterics. So if you have something that sterics is a problem, para wins. As it turns out for halogens, para is slightly favorable because remember, this group, it's not Cl+, it's Cl+ with this giant planet of iron and trichloride. The electrophile is a very large beast relative to the benzene just based on atomic size. So in halogenation, this guy kind of wins. Alkylation, it's actually about 50-50 in this case. The carbocations are pretty close in density. And the thing that happens here is while there's a bit of a steric bump for the ortho, there's a bit of a probability bump for the, there's a steric bump for the para. There is a probability bump for the ortho. Two orthos will help you react, but para is going to be sterically favored. So it ends up being pretty close to 1-to-1. All right, that's where we're going to break today, guys. We'll do the after-class stuff. I'll see you guys on Friday. Okay, so let's follow up with some of these other follow-up questions. Now, if we're asked to evaluate the impact of, let's say, a methyl group, we can't go through, as we did before, and draw, let's say, clear-cut resonance structures. The methyl group on its own has no pi electrons, so it's not like we can draw resonance structures where pi electrons are donating into this. So that's the first indication. In terms of resonance, it really has no impact because an alkyl group of a kind like this really doesn't have pi electrons to donate, so it's really a neutral sort of impact. There's no benefit, plus or minus, to having an alkyl group on the ring. However, we usually rank a alkyl group as inductively activating. So by induction, it's a donor. And that's, again, explained via hyperconjugation. The example we've used before is if you imagine, let's say, an aldehyde versus a methyl group on both sides, like a ketone. These can be considered, or you can imagine the single bond resonance structure, negative and plus, as like a carbocation-like structure compared to the ketone, negative and plus, where you have your CH3 groups on both sides. So the impact or the benefit, hyperconjugation, which is sort of in line with kind of like an inductive type behavior, is donating charge density to help stabilize the center, versus here we only have one hyperconjugation group helping. That's why we say that the aldehyde is more reactive, the ketone is more stabilized because of this sort of issue. Now, a similar thing is happening here, but it's most easy to visualize if, let's say, we were to form the sigma complex. Let's for a second say I'm going to add to the ortho position of my group. I'm going to use an electrophile to add to that position and just draw what the consequence might be. So if I have my methyl group here, I have added to the center with my electrophile, and I've created this structure here, right? It's this carbocation, which is one possible resonance structure, and then delocalizing that out, that sigma complex would also look like here, positive charge, hydrogen and electrophile with my methyl, and one last move to make this one, methyl, hydrogen, and electrophile. So the point is, we have this resonance structure here, or the overall delocalized structure of the carbocation allows for the positive charge to build up immediately adjacent to a donor. So it's going to be an overall activator because we have inductive donating. There's a bit more electron density because of this donation ability. And what kind of director? We expect it to be an ortho-para director because in addition to either the ortho or para position, we'll create a resonance structure with the positive charge immediately adjacent to the donating nature of my, my methyl group. Now, if we're going to evaluate, let's say, a ketone or a carbonyl, this one we can potentially draw this out as a resonance structure. So you could potentially imagine, let's say we did this. If I were to pull off electron density out onto the carbonyl, it's sort of like an extended keto or enolate type structure. So if we were to do that, that's going to leave behind positive charge here, double bond, O minus, like that. And that positive charge can be delocalized around the ring into our representative structures that we're used to seeing, right? This kind of 1, 3, 5 type geometry. Like this. Oops. Like this. So these three point to positive charge building up at these three positions, which relative to the group in question, what we're evaluating here, that means we're going to have sort of a delta plus here, here, and here, really just as a result of having this group on this position here. So via resonance, it's withdrawing group. So it's pulling electron density out of that ring by having resonance structures which actually induce a positive charge somewhere on the ring. And via induction, it's a weak withdrawing group. So it's weakly withdrawing. Because what's happening, again, remember this center here is effectively delta plus, or at least in the carbonyl. You remember that's our electrophilic center, and there's a bit of an inductive behavior. It's less, more electropositive here, so they're going to have an inductive withdrawing through the sigma bonding skeleton as well. So overall, we expect this to be deactivating because we're pulling electron density out of the ring. What kind of director is it going to be? Remember here, if we're actually creating these centers of partial positive charge, it's less likely that an electrophile and electropositive center would actually attack at that point. This will be a meta director as a function of that. Getting away from something where it has to do that addition to these three centers here is would be favorable overall. So just reiterating against this is also what we discussed in class. This guide here is probably one of the most important ones to help summarize everything. If we take our benzene as a reference point, the weakly donating groups, such as our methyls, are first. OME, where we've actually got a lone pair and, which is both the pi donor, but then also sigma withdrawing, that sort of sets up here. The nitrogen is less electronegative, so it's less of a sigma withdrawing, but it's actually a pretty good pi donor. And then the O minus, very strong pi donor, and that sort of gives you this ranking order as we go through here. On the other side, remember our halogens are kind of weird ones. They are both withdrawing and donating, so while they are mildly deactivating, they are still ortho-para directing. All the other ones down here, they're deactivating enough that they really slap us into our meta-directing kind of part. So the substitution we'd expect here would be at these meta positions. Other ones, these would be ortho-para, no selectivity across this one, or at least we cannot have the ortho-para nomenclature. Ortho-para here, 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 and here. And actually remember there's 2 ortho positions each, so you can actually designate across all of those. Those are the sites that we expect to see with that substitution. Okay, so with this, if you imagine starting out with the group that's given, we're doing the electrophile shown here. In this case, the first one is chlorination. What you would do is first evaluate the group that we have here. This is a carbonyl. That carbonyl, remember if you go back to our chart, carbonyls stack up as mildly deactivating and meta-directing. And that would give us, we can show this out discretely, an intermediate. Our prediction here would be to have something like this at the meta position specifically. So it's like that. That would be our preferred product where we have meta. And we can evaluate this indirectly. Let's, for example, say I'm going to draw the sigma complex where I'm comparing addition to, let's say, the ortho position as compared to addition to the meta position. Okay, so ortho position, hydrogen, chlorine, like this, with double bond aldehyde and a positive charge localized right here. Now this is a very unfavorable interaction because we have a positive charge right next to this electron withdrawing center. That's going to hurt that one quite a bit. As a result, if you look at the meta substitution, let me just bring that down a bit. So if we have our carbonyl, I'm going to add to that meta position first. That gives me hydrogen, chlorine, and I'm going to have, let's say, a positive charge here, like this. Now, if I permute that positive charge around the ring, it will exist here, here, or here. And you notice that in this case, there's never a case where the positive charge is immediately on the carbon adjacent to this ring. The ortho para position, that is not the case. We will have a case where the positive charge is directly onto it. So that's going to hurt this one and make the meta position or meta directing more favorable. In the bottom example, once again, look at what you're using. This is a methyl group on the ring. Going back to our chart, methyl are mildly activating and ortho-para directing. That's just a result of alkyl groups being donor type groups. So if we're donating into this ring, we expect this to be an ortho-para type system. So the products we would expect here would be our methyl and acylation at that position. And we would also get the one where we have a para-substituted product, like that. Once again, you can go through that process. The intermediate we get by attacking at that ortho position. We would have our methyl group. We've added to this compound to give us the following sigma complex, and that has its favorable interaction here with the positive charges being partially stabilized. It's like a tertiary carbocation by having that methyl group present. And as before, we're going to have this delocalization at these three centers. So the same thing happens where if I were to add to the para position, it would give me a positive charge that would also have resonance at that point. So that gives us these two as our stabilized products.